Good afternoon, everyone. Welcome to the talk of our paper CLUTTR, a diagnostic benchmark for inductive reasoning from text. So, why do we need yet another question answering datasets? We already see a deluge of question answering datasets in the literature and it's ever growing. But a lot of these question answering datasets rely on what we call as extractive reasoning. So when I say extractive reasoning, I mean that they rely on pattern matching because the answer is already present in the document. For example, squad. But they rely also heavily on the linguistic artifacts, and that's why they have been shown to be brittle to adversarial examples when you essentially change a sentence and then the model gets confused and gives you back a wrong answer. So, since they rely heavily on the linguistic artifacts, a pre-trained language model such as BERT almost always outperform every other baseline. So it's clear that we need tasks which look for a much more higher order reasoning. So essentially we need tasks that rely less on the language modeling or they rely less on the linguistic artifacts of the text, but they work more on the abstract reasoning component. Basically, we need tasks which require us to move away from the language model pre-training, and those tasks we need to look for that push for generalizability and that helps us to evaluate for robustness. Recently, there is a growing interest in models that are capable of logical induction and combinatorial generalization, and we need tasks which evaluate the logical induction component also because that leads to generalization and much better robustness. Thus, our proposal, CLUTTR. So, CLUTTR is a game of deducing family relations from text. This setup has been used extensively in knowledge-based completion tasks and in inductive logic programming. However, in knowledge-based completion, they work on the subsymbolic representation for entities and relations. In our dataset, the task is to learn the compositional relations directly from the text. So, our task focuses on inductive reasoning. Basically, the answer is not provided in the document, and the model has to figure out the answer after actively reading the entire text. So, the stories that we generate has an underlying kinship graph which is constructed by applying the logical rules of our world. Thus, each story has a proof state and is consistent across the world of the dataset. The challenge is to learn the underlying logical rules of the kinship relations, such as transitivity or reflexivity or symmetry. The task is proposed as follows. The task consists of a story and a query, and we have to predict the answer, which is one of the relation among various relations available in the world. Now the query is in the format of a simple entity pair format. So essentially it's a tuple which contains two entities, and the task is to figure out what is the relation between these two entities. Now this is essentially a diagnostic suite. It contains various tunable parameters so that you can generate the data for different control test cases. So let us look at the data set. So this is essentially a kinship game. So given a document, you have to first read the document and then find out what is the relation between the two entities. So in this document, we see that it describes a relationship between Charles and David and a relationship between Randolph and David, and it is essentially in the format of a story. And this story has been created by paraphrasing from Amazon Mechanical Turkers. Now, the model has to figure out the answer of this story, which is essentially brother. Thus, in this task, we have an input document. We also provide the underlying graph, which is the underlying kinship graph of the story, which is not used for the task, but it is just used as a reference for users to inspect their model performance. And the query is in the form of an entity tuple, and we also provide the used rule so that users can inspect the proof trace of the particular story in order to find out where their model didn't perform well. So let us first look at the data generation overview. So we have essentially a predefined rule base of the composition of kinship relations, such as son and son gives us grandson, and sibling of a sibling is a sibling. Now, this set of rules are very small and handcrafted set of rules. We have deliberately kept it small because we didn't want to introduce ambiguities so that our human raters gets confused. So that this is the main distinction, that the rules that we use may not necessarily need to conform with the kinship rules that we know in our real world. These are much more restricted set of ideal rules that we want to use in our stories. So essentially, we generate a random kinship graph which satisfies the rules in our knowledge base. We sample a target fact, which is the target to predict, and then we apply iterative backward chaining to sample a set of facts that can be used to prove the target relation. So essentially, with this set of facts, we convert them to a set of sampled facts to a set of natural language story by applying the paraphrases that we have collected from Amazon Mechanical Turk. So what are the tasks that are available in CLUTTR? So one of the main tasks that we focus on is systematic generalization. So what is systematic generalization? It is the algebraic capacity to understand and produce a potentially infinite number of novel combinations from known components. Essentially, if you are given a test distribution which is different from the training distribution, if the test distribution is built from the same production rules, then one can hope to infer the results in the test set systematically. A system in an ideal case should be able to disentangle the production rules from the data and hence infer any and all cases of data which had resulted in the combination of such rules. Therefore, since the stories have an underlying kinship graph, we provide a test set for explicitly testing systematic generalization. So in the first case, we provide stories that have an underlying graphs of length k equal to 2 and 3, where k equal to 2 represents the combination of all possible relations in a 2-hop setting, and 3 represents the combination in a 3-hop setting. And during testing, we provide some unknown combinations of 3-hop setting for the models to figure out which is the relation. But then we can extend this logical generalization to a much more complex logical generalization where we provide larger and larger combinations of relations while we provide a smaller combination of relations in the training set. So essentially, just by looking at the training set, a model should be able to disentangle the rules and then reapply the rules to get to the correct answer for any large test cases. So these are essentially the underlying graphs, but we provide to our natural language understanding models a complete story which is created by applying the Amazon Mechanical Turk paraphrases on this underlying graph. So since we apply the paraphrases, we have another level of generalization which we call as linguistic generalization, where we use different Amazon Mechanical Turk paraphrases for the same graph in training and test time. So as I was saying, that the current question answering datasets mostly rely on the linguistic artifacts of the dataset. Here, to explicitly remove that reliance, we have provided different Mechanical Turk paraphrases meaning the same thing but on the same graph so that you can test for linguistic generalization as well. Now we provide our dataset to human Turkers and then we want to see how they perform on our dataset. So in this graph, we provided human Turkers a limited time, that is 5 minutes, and then we see that as and when we increase the number of hops of resolution of the underlying graph, the Turkers get less and less confidence in answering the correct relation. However, when we provide human Turkers with unlimited time, everybody gets correct answer. because given our story, if you are given a pen and paper and then asked to solve such a story, you will be able to solve it in X number of time. So the human Turkers also report increasing difficulty of the tasks. We also have another vertical that we call as robustness of reasoning. So since the stories have an underlying logical rules, so we can generate such stories which have distractor rules or distractor facts. For example, either we can provide a supporting fact which provides a supporting path, that is additional information for resolving the current clause or the current task. Then we can also provide an irrelevant fact, which is essentially a distractor path which could distract the model from resolution of the current task. And then we can just provide a disconnected fact which has nothing to do with the resolution of the current query. So what are the key research questions that we are looking for? We want to test whether the natural language understanding models compare in terms of systematic generalization. We also want to see the performance of a graph neural network that has access to the underlying graphs, and that should become the upper baseline to see the difference between the effectiveness of current natural language understanding models with a graph-based model. And we also want to test how robust these models are with the addition of noise facts given to a story. So we have a bunch of baselines. We have a set of baselines for natural language understanding, and we have one baseline for graph. So that is the graph attention networks, which is one of the state-of-the-art models for many graph prediction, link prediction, and node prediction tasks. So we have chosen a set of text understanding models which have been shown like good performance in current state-of-the-art data sets. So the details of implementation of these models can be found in our paper. So let's see what the results are. The main results of our paper is on the systematic generalization. On the left-hand side, you see the performance when we have trained the models with stories containing 2 and 3 hops of underlying relations. And then on the right-hand side, you see the graph where we have trained the model with 2 and 3 hops of underlying kinship graph and the text story on top of it. So you see that the graph attention networks gets a massive jump when they are trained with more and more support. So that means that they have access to more and more support of the underlying graph, and since they don't have to do any parsing or resolution, they are performing really well in the generalization test. Although all the models, including the graph attention network, they fail on generalization on larger and larger combinations, which means that none of the models now can disentangle the underlying rules from the given data. But still, we have a lot of grounds to cover for our natural language understanding models if they are able to extract or disentangle the linguistic artifacts from the relations. So what happens when we provide the same linguistic artifacts or the same Amazon Mechanical Turk paraphrases in training and test time? Then we saw that the gap have reduced between the graph attention network and all the natural language understanding models. So this reinforces our belief that the current natural language understanding models mostly rely on the linguistic artifacts and not perform reasoning on top of it. So we also tested for robustness in reasoning, and we found out that memory attention compositional networks from Hudson and Manning, this model performed overall better among all the natural language understanding models in the reasoning test, in the robustness of the reasoning test. But still there is a lot of ground to cover between the language models and that of the graph attention network, which performs almost perfectly in a lot of scenarios. Although in some scenarios, the text-based models perform better when they are trained with clean setup, but then they are tested on the supporting facts. They exploit on the language cues of the supporting facts and derive the answer, but then the graph attention networks prove to be really sensitive to the addition of cycles if they are not being trained to it. But overall, the graph attention networks have higher test accuracy when they are trained with the noisy facts, and this training of the noisy facts are not taken into account by the natural language models whose performance decrease. So the key takeaways of our study is that we need structure or inductive biases in our models to perform better on generalization and robust reasoning. The natural language understanding models must try to represent the inductive bias or structure internally. Systematic generalization is hard because we saw the result, and we need more research in representing the compositional and modular networks and also to disentangle the rules from the given data. Logic provides a provable way to devise datasets for such a semantic task, and we propose our model or our dataset CLUTTR, which is a diagnostic suite to test on wide range of control test cases. And since it's a diagnostic suite, you can generate the data on various different noisy and cleaning test sets or even on generalization tests to explicitly test where your model performs better or where your model fails. So thank you for attending the talk. This work would not have been possible without my amazing collaborators, Shagun, Jin, Joel, and Will. If you have any questions, please feel free to contact me. The code is available on GitHub, and the website and the paper are also on the archive. So feel free to contact me if you have any questions. Thank you for attending the talk.